A neutral conductor can indeed be overloaded on a single-phase service. If the neutral conductor carries more current than its rating allows, overheating and a potential fire hazard can occur. There are several scenarios where a neutral might become overloaded. Firstly, an unbalanced electrical system where more current flows on one phase compared to the other can cause this. Secondly, nonlinear loads, such as electronic devices, draw current impulses which can generate harmonics on the electrical line. Thirdly, loose connections or programs can allow unintended current flow through the neutral conductor. Nonlinear loads, exemplified by electronic devices, draw current impulses, and these pulses create harmonics on the electrical line. These harmonics can then travel back through the neutral conductor, potentially leading to an overload. An overloaded neutral can have several serious consequences. Firstly, there is the risk of fire hazard. The overheated neutral conductor can ignite surrounding materials. Secondly, equipment failure can occur. Overheating can damage electrical equipment connected to the circuit. Thirdly, voltage drop can be a problem. The increased current flow through the neutral can cause a voltage drop, leading to reduced power quality. Fourthly, intermittent outages can occur. An overloaded neutral can trip circuit breakers or blow fuses, causing interruptions in power supply. Preventing neutral overloads is vital, and there are several steps to achieve this. Firstly, balance electrical systems to ensure equal current flow on all phases. Secondly, install dedicated neutral conductors for heavy loads such as electric motors and transformers. Thirdly, use surge suppressors and other protective devices to reduce harmonics generated by nonlinear loads. Regularly inspect and maintain electrical systems to identify and correct any issues that could lead to neutral overloads. Understanding the behavior of current in single-phase circuits is essential for grasping the potential for neutral overload. In a balanced single-phase circuit, the current flowing in the hot wire returns through the neutral wire. Ideally, these currents should be equal and opposite, resulting in minimal current in the neutral. However, imbalances and nonlinear loads can disrupt this balance. Imbalances occur when the loads connected to each leg of the single-phase service are unequal. For instance, if one leg is supplying a heavy appliance while the other leg powers only a few lights, a significant current difference arises. This difference in current then flows through the neutral wire, potentially exceeding its capacity. Nonlinear loads further complicate matters. Traditional linear loads, like incandescent bulbs and resistive heaters, draw current proportionally to the applied voltage, creating a sinusoidal current waveform. However, many modern electronic devices, such as computers, LED lighting, and variable frequency drives, are nonlinear loads. These devices draw current in short, sharp pulses, distorting the current waveform and introducing harmonics. Harmonics are multiples of the fundamental frequency of the alternating current, which is typically 60 Hz in the United States. These harmonic currents can add up in the neutral conductor, even if the loads appear to be balanced. The third harmonic, in particular, is a significant contributor to neutral current. In a three-phase system, the third harmonic currents tend to cancel each other out in the neutral. However, in a single-phase system, they add directly, increasing the load on the neutral conductor. To mitigate the risk of neutral overload, it's crucial to consider several factors during the design and installation of electrical systems. Firstly, proper load balancing is essential. Distribute loads evenly across the available circuits to minimize current differences. This involves carefully planning the placement of appliances and equipment to ensure that no single circuit is excessively burdened. Secondly, use appropriately sized neutral conductors. The neutral conductor must be able to handle the anticipated current load, including the potential contribution from harmonics. The National Electrical Code, or NEC, provides guidelines for determining the appropriate conductor size based on the expected load and other factors. Thirdly, consider using dedicated neutral conductors for circuits with significant nonlinear loads. This helps to isolate the harmonic currents and prevent them from affecting other circuits. Fourthly, employ harmonic filters to reduce the harmonic content in the electrical system. These filters are designed to attenuate specific harmonic frequencies, thereby reducing the load on the neutral conductor. Fifthly, regularly inspect and maintain electrical systems. Check for loose connections, damaged wiring, and other potential problems that could contribute to neutral overload. Infrared thermography can be used to identify hotspots, which are often indicative of overloaded conductors or connections. It is important to size the neutral conductor correctly. The NEC specifies requirements for sizing neutral conductors based on the type of load and the service voltage. For example, NEC Article 220.61 provides guidance on calculating the neutral load for household ranges and electric clothes dryers. For nonlinear loads, the NEC requires that the neutral conductor be sized to carry the maximum neutral current, including the harmonic currents. In some cases, this may require increasing the size of the neutral conductor beyond what would be required for a linear load. Furthermore, it is crucial to understand the impact of voltage drop on neutral conductors. Excessive voltage drop can lead to reduced power quality and equipment malfunction. The NEC provides guidelines for calculating voltage drop and ensuring that it remains within acceptable limit. In addition to the NEC, other standards and regulations may apply, depending on the specific location and application. It is essential to consult with a qualified electrical engineer or inspector to ensure that all applicable requirements are met. Consider the impact of shared neutral conductors. In some cases, multiple circuits may share a common neutral conductor. While this can save on wiring costs, it also increases the risk of neutral overload. When multiple circuits share a neutral, the neutral conductor must be sized to carry the combined current from all of the circuits. This is particularly important when the circuits serve nonlinear loads. Another important consideration is the grounding of the electrical system. A properly grounded system provides a low impedance path for fault currents, helping to protect against electrical shock and equipment damage. The grounding system must be designed and installed in accordance with the NEC and other applicable standards. Also, be aware of the impact of power factor correction on neutral current. Power factor correction capacitors are often used to improve the efficiency of electrical systems. However, these capacitors can also generate harmonic currents which can increase the load on the neutral conductor. It is important to carefully evaluate the impact of power factor correction on neutral current before installing capacitors. Understanding the different types of nonlinear loads is also beneficial. Some common examples of nonlinear loads include computers, electronic ballasts for fluorescent lighting, variable frequency drives, and uninterruptible power supplies. Each of these types of loads has a unique harmonic signature, which can affect the neutral current in different ways. Furthermore, consider the impact of energy-efficient lighting on neutral current. While energy-efficient lighting, such as LED lighting, can save energy, it can also generate harmonic currents. It is important to select energy-efficient lighting products that have low harmonic distortion. Another important consideration is the use of surge protective devices. Surge protective devices can help to protect electrical equipment from damage caused by voltage surges. However, some surge protective devices can also generate harmonic currents, which can increase the load on the neutral conductor. It is important to select surge protective devices that have low harmonic distortion. The proper installation and maintenance of electrical equipment is also essential for preventing neutral overloads. Loose connections, damaged wiring, and other defects can contribute to excessive neutral current. Regular inspections and maintenance can help to identify and correct these problems before they lead to a neutral overload. It is important to use appropriate wiring methods. The NEC specifies different wiring methods for different applications. It is essential to select a wiring method that is appropriate for the specific load and environment. Furthermore, consider the impact of ambient temperature on conductor ampacity. The ampacity of a conductor decreases as the ambient temperature increases. It is important to direct the conductor ampacity accordingly to ensure that it can safely carry the intended load, and ensure the system is properly labeled. All electrical equipment should be properly labeled to indicate its voltage, current, and other important information. This helps to ensure that the equipment is used safely and effectively. Also, consider the use of isolated ground receptacles. Isolated ground receptacles provide a separate grounding path for sensitive electronic equipment. This can help to reduce noise and improve the performance of the equipment. Furthermore, be aware of the impact of electromagnetic interference, or EMI, on electrical systems. EMI can cause a variety of problems, including interference with electronic equipment, data corruption, and even equipment damage. It is important to take steps to mitigate EMI, such as using shielded cables and filters. Another important consideration is the use of uninterruptible power supplies, or UPSs. UPS provide backup power in the event of a power outage. However, some UPS can also generate harmonic currents, which can increase the load on the neutral conductor. It is important to select UPS that have low harmonic distortion. Review the NEC tables carefully. The NEC contains numerous tables that provide guidance on conductor ampacity, overcurrent protection, and other important electrical parameters. It is essential to consult these tables when designing and installing electrical systems. For example, NEC Table 310.15b16 provides ampacity ratings for insulated conductors. NEC Table 430.52 provides guidance on motor overcurrent protection. Understanding the difference between grounded and ungrounded systems is also crucial. In a grounded system, one of the conductors is intentionally connected to ground. In an ungrounded system, none of the conductors are connected to ground. Each type of system has its own advantages and disadvantages. Furthermore, consider the impact of high-resistance grounding on neutral current. High-resistance grounding is a method of grounding that limits the amount of fault current that can flow in the event of a ground fault. This can help to reduce the risk of electrical shock and equipment damage. And be aware of the impact of arc flash hazards. Arc flash is a dangerous electrical phenomenon that can occur when a fault current flows through the air. Arc flash can cause severe burns, blindness, and even death. It is important to take steps to protect against arc flash hazards, such as wearing appropriate personal protective equipment and using arc flash rated equipment. Additionally, consider the use of ground fault circuit interrupters, or GFCIs. GFCIs are designed to protect against electrical shock by detecting small amounts of current leakage to ground. GFCIs are required in many areas, such as bathrooms, kitchens, and outdoor locations. And always follow the manufacturer's instructions. All electrical equipment should be installed and maintained in accordance with the manufacturer's instructions. This helps to ensure that the equipment is used safely and effectively. Be mindful of the impact of voltage imbalances on neutral current. Voltage imbalances can cause excessive current to flow in the neutral conductor. It is important to correct voltage imbalances to prevent neutral overloads. The NEC provides guidance on voltage balance in section 210.11. Consider the use of harmonic mitigating transformers. Harmonic mitigating transformers are designed to reduce the amount of harmonic current that is generated by nonlinear loads. These transformers can help to prevent neutral overloads. Also be aware of the impact of transient voltage surge suppressors, or TVSS, on neutral current. TVSS devices are designed to protect against voltage surges caused by lightning strikes or other events. However, some TVSS devices can also generate harmonic currents, which can increase the load on the neutral conductor. Finally, remember to consult with a qualified electrical engineer or inspector. Electrical work can be dangerous. It is important to consult with a qualified electrical engineer or inspector to ensure that all work is performed safely and in accordance with applicable codes and standards. Understanding the principles of three-phase power is also helpful, even when working with single-phase systems. A three-phase system consists of three alternating current waveforms that are offset by 120 degrees. This configuration provides a more stable and efficient power supply than a single-phase system. While single-phase systems are commonly used in residential and small commercial applications, three-phase systems are typically used in larger commercial and industrial facilities. Knowing the differences between delta and Y configurations in three-phase systems is also important. In a delta configuration, the three phases are connected in a closed loop. In a Y configuration, the three phases are connected to a common neutral point. Each configuration has its own advantages and disadvantages in terms of voltage, current, and fault current characteristics, and being able to calculate the line-to-line and line-to-neutral voltages in a three-phase system is useful. The line-to-line voltage is the voltage between any two of the three phases. The line-to-neutral voltage is the voltage between any one of the phases and the neutral point. Understanding these voltage relationships is essential for properly connecting and operating three-phase equipment. Furthermore, understanding how to measure current and voltage in electrical circuits is beneficial. Ammeters are used to measure current while voltmeters are used to measure voltage. These instruments can be used to monitor the performance of electrical circuits and identify potential problems. There's also the importance of understanding the concept of impedance in electrical circuits. Impedance is the total opposition to current flow in an alternating current circuit. It is composed of resistance, inductance, and capacitance. Understanding impedance is essential for analyzing and designing electrical circuits. Knowing how to use a multimeter is also useful. A multimeter is a versatile instrument that can be used to measure voltage, current, resistance, and other electrical parameters. It is an essential tool for any electrician or electrical engineer. And understanding the different types of circuit breakers and fuses is important. Circuit breakers and fuses are used to protect electrical circuits from overcurrents. Circuit breakers can be reset after they trip, while fuses must be replaced. It is important to select the appropriate type and size of overcurrent protection device for each circuit. In addition to the NEC, other organizations such as the Institute of Electrical and Electronics Engineers, or IEE, and the National Fire Protection Association, or NFPA, publish standards and guidelines related to electrical safety and design. It is important to be familiar with these resources. Continuous learning is also essential. The field of electrical engineering is constantly evolving. It is important to stay up to date on the latest technologies, codes, and standards. This can be achieved through continuing education courses, professional conferences, and industry publications. In addition to technical knowledge, good communication skills are also important. Electrical engineers and electricians often need to communicate with other professionals such as architects, contractors, and building owners. It is important to be able to clearly and effectively explain technical concepts to non-technical audiences. Always prioritizing safety is paramount. Electrical work can be dangerous. It is important to always follow safe work practices and use appropriate personal protective equipment. Remember to always energize circuits before working on them. And never work alone. Finally, remember that electrical safety is everyone's responsibility. By following safe work practices and adhering to applicable codes and standards, we can all help to prevent electrical accidents and injuries.